pause for a second and think about this. Scientists just made a metal that learns. Not a computer chip. Not a machine. A piece of actual metal that remembers, adapts, and responds like it has a nervous system of its own. This isn't a lab curiosity. It's a line in the sand for 2025, when matter itself starts to think. And if you understand what that means, you can see where the next decade of technology is heading before anyone else does. My team at FutureForge Explored has been tracking this breakthrough for months, long before it made it out of classified reports and research journals. These are the same networks that tipped us off about NASA's shape memory alloys and DARPA's self-repairing robotics projects before they went public. And this is exactly why FutureForge subscribers don't just follow the future. They get there first. Here's what nobody's talking about. This so-called thinking metal doesn't use electronics at all. It processes and stores information inside its own atomic structure. Think about that. Memory without a computer chip. When you stress these alloys, they don't just bend. They rearrange their internal dislocation networks. Tiny defects in their crystal lattice that act like synapses in a brain. Over time, they literally remember the patterns of force you applied and adapt how they respond. The foundation of this revolution comes from shape memory alloys. Metals like nickel titanium that can be trained to return to a specific shape after being deformed. But the latest generation goes far beyond that. NASA and its partners have pushed these materials to survive extreme temperatures, carry heavier loads, and react faster than ever before. We're talking about alloys that can remember their training even at 500 degrees Celsius. Why does this matter? Because we're no longer talking about materials as passive components. These metals act more like living systems, self-adjusting, self-healing, and capable of learning over time. That changes everything about how we build spacecraft, robotics, even infrastructure. But here's where it gets even more interesting. Scientists have now built entire neuromorphic networks out of these metals. Structures that don't just store memory, but exhibit behavior eerily similar to a biological brain. If you're wondering how far this goes, here's the part nobody's ready for. Researchers have built metallic networks that can actually learn, forget, and even display alertness states, without a single microchip. In one landmark experiment, silver nanowires were arranged in sprawling networks where each junction acted like a synapse. When voltage was applied, these networks struggled to find the best pathways for current, a process that eerily mirrored how neurons fire and adapt in the human brain. The result? Emergent intelligence, not coded, not programmed, arising from the raw physics of metal. Thousands of these junctions working together create behaviors we used to think required biological tissue. This is neuromorphic computing at the materials level. And it's not just a lab trick. Tests at Sandia and Texas A&M showed these metals could remember stress patterns with 85% retention over 1,000 cycles, self-heal microscopic cracks, and adapt their mechanical responses over time. That means one thing. We're entering an era where materials don't just perform tasks, they evolve. Imagine a robot with joints that get stronger the more they're used. Or a spacecraft skin that learns to absorb and deflect micrometeor impacts after each collision. This isn't speculative anymore. It's being validated in peer-reviewed studies and high-security defense projects right now. But here's the real question. How do we manufacture intelligence directly into metal at scale? Let me show you how they're actually making this work. Traditional metallurgy wasn't enough, so scientists reinvented how we create metals. At Texas A&M, researchers are using AI-driven optimization to design new alloys in months instead of decades, running simulations that test thousands of possibilities before a single sample is forged. It's materials discovery at warp speed. The manufacturing toolkit is just as radical. Directional solidification lets them grow crystals in controlled ways. forming built-in dislocation networks that act like memory nodes. Nanoscale doping, precisely adding trace elements, enhances the way metals store and process information. Additive manufacturing, or 3D printing, gives engineers the ability to design internal neural pathways into the metal's structure itself. And then there's thermomechanical training, literally cycling these metals through stress and heat until they develop and lock in complex behavioral responses. The results are staggering. Metals that retain response patterns with 85% accuracy after 1,000 stress cycles. Alloys that self-heal nanoscale cracks before they grow. Materials that adapt their stiffness with 40% faster reaction times after learning. These aren't one-off lab curiosities. They're engineered systems designed for real-world deployment. And here's the kicker. Some of these processes are already compatible with aerospace and defense manufacturing pipelines, meaning we could see intelligent metals inside working machines far sooner than anyone expects. But knowing how to make these materials is only half the story. The real disruption comes when you see where they're being deployed first. This is where the implications hit hard. NASA's already using intelligent metals in its span-wise adaptive wing program, successfully folding F-18 wing sections in flight without a single hydraulic actuator. That means lighter aircraft, fewer failure points, and systems that literally reshape themselves midair. DARPA's pushing even further, funding self-reconfiguring robots and adaptive camouflage systems that use color-changing, shape-shifting materials instead of complex electronics. In robotics, Boston Dynamics and others are exploring metallic joints that sense their own stress and adjust stiffness in real time. Imagine a robot that becomes more agile with every movement. Not because of new code, but because its body learns mechanically. And for infrastructure, self-healing bridges and adaptive building frameworks are now moving from concept to prototype. We're talking about metal that closes microfractures before they become catastrophic failures, potentially saving billions in maintenance and extending the lifespan of critical systems by decades. This isn't just a technical leap, it's an economic one. The smart materials market is projected to hit nearly $150 billion by 2032, with intelligent metals leading the charge. And here's what few people realize. The first adopters, defense contractors, aerospace giants, advanced robotics labs, are locking in capabilities years before this tech even reaches the public sector. In other words, the race to control intelligent matter has already begun. But if this sounds like pure upside, stay with me, because the next part is where the ethical, economic, and even existential challenges come crashing in. Here's what nobody's talking about. The economics of intelligent metals are as disruptive as the science. Right now, these alloys cost nearly $1,000 per kilogram in research quantities. But that won't last. With AI-driven design and scale production, costs are projected to drop by more than 60% in the next 5 years. And when that happens, industries from aerospace to construction will rewrite their cost models. Imagine cutting maintenance costs in robotics by 60%, or doubling the lifespan of critical infrastructure without adding a single new part. That's billions in unlocked value, but disruption always comes with friction. Scaling these materials to industrial volumes is a massive engineering challenge. Training protocols for neuromorphic metals aren't standardized yet. Memory drift, how these metals forget over time, still needs to be solved. And then there's the ethical layer. What happens when materials can self-modify in critical systems? Who's liable when an autonomous bridge, robot, or aircraft makes decisions based on its own experience? These aren't hypothetical questions. Regulators, defense agencies, and manufacturers are wrestling with them right now. And if you're wondering how fast this could escalate, consider this. The convergence of AI, neuroscience, and materials science is driving toward programmable matter, metals that reconfigure themselves on command. That's not science fiction. It's the logical next step in a world where matter doesn't just respond. It learns, evolves, and adapts. Which brings us to the real question. Are we building tools, or are we creating a new class of autonomous entities? The answer will define the next decade of engineering, defense, and ethics in ways we can barely imagine. So here's where this gets real. The race isn't just about making smarter materials. It's about who controls them. Right now, DARPA, NASA, and private aerospace firms are pouring billions into integrating these metals into aircraft, satellites, and autonomous systems. And when metals can heal themselves, adapt their properties mid-mission, or even reconfigure for entirely new functions, you're not just replacing components. You're rewriting the rules of engineering itself. My forecast? Within a decade, programmable metals won't be exotic. They'll be foundational. Buildings that adapt to earthquakes in real time. Aircraft that repair themselves mid-flight. Robots that no longer need complex sensors because their very structure feels and responds. And here's the kicker. The companies who master this first will hold the keys to entire industries. So I'll leave you with this. When matter itself starts thinking, where do we draw the line between tool and entity? Drop your thoughts in the comments, and if you want to stay ahead of breakthroughs like this, before they hit the headlines, hit subscribe. The future isn't coming. It's already here. And at Future Forge Explored, we're decoding it together.